Alright, hello. You guys are sitting here in Austin, New Jersey, and I'm not. Haha. So here is the lesson for Monday or Tuesday or the weekend, whenever you decide to get to it. Also take note, I'll just put an updated schedule up on the Ning too so you can see what we're doing and so you know what to expect next week. So this is section 9.3. It's called error because we're going to try to quantify the amount of error that a series has if you only give it a limited amount of terms. So we're going to start with a geometric series. We're going to take the geometric series 1 minus x squared. And let's look at that series. We probably already figured out what the series was for it somewhere in our notes. But we know it's geometric because it follows that 1 over 1 minus r idea. So in this case we know that the a value is 1 and the r value is x squared. So if we want to write our series, we'll start with 1 and we'll multiply each term by x squared. So my series for 1 over 1 minus x squared would be 1 plus x squared plus x to the 4th plus x to the 6th and so on and so on and so on. I'm going to cut this off at my 4th partial sum. It's not a 4th degree polynomial like when we've been talking about the Taylor series. It's a 4th partial sum, meaning I have 4 things. That's my phone. Okay, sorry, I pushed silent. So anyway, if we have this series and we only look at its 4th partial sum, meaning we're just looking at the first 4 terms of the series and I cut it off, at this point I know that there's some error because I'm only looking at a small part of the series. The series goes on forever, x to the 8th, x to the 10th, x to the 12th, forever. So if I don't have every single term listed, I'm not going to have a total match between the series written out this way and the function written out this way. So at some point, they match up, but then at some point they start to diverge away from each other because I don't have an infinite number of the terms written down. So I cut this off at the 4th partial sum. I wrote, you could be asked to cut it off anywhere in a problem that you might be looking at. Well, this error, the amount I cut off, the amount I threw away, I'm going to call it r sub n, the remainder. And r sub n is basically just picking up where the series left off. I went for the first 4 terms. My next term would be x to the 8th in my series. So I'm going to start off my remainder by saying, well, the remainder would start with x to the 8th, and then it would include x to the 10th, x to the 12th, x to the 14th and 16th, and so on, and it would go on forever. So this remainder is actually the amount of the series that I cut off. It starts at x to the 8th, and it keeps going on forever, and it's the amount that I didn't use in my original series. That remainder is actually another new geometric series. It starts with x to the 8th, and every term just gets multiplied by x squared. So my remainder, r sub n, can be written as another new geometric series where the first term is x to the 8th and r, the multiplier, is x squared. So if I just take r to the n and rewrite that in a series notation, or think about it as a geometric series, we know that the sum of a geometric series, geometric again, not Taylor, geometric, is a over 1 minus r. So that remainder can be rewritten as a over 1 minus r. A being x to the 8th, that's my new first term, and x squared being the r term, what I'm multiplying each one by. So the remainder can actually be quantified as x to the 8th over 1 minus x squared. What that means is I can take any x value and plug it into that remainder equation and figure out how much error there is at that x value. So let's say at x equals 0.2. The error, meaning the difference between the actual function and the series we're trying to get to match up with it, is this. It's my remainder formula that I just figured out, taking it and plugging 0.2 in for x. When I plug 0.2 in for x, I get this. Really tiny, telling me that when x is 0.2, my error is really, really, really small. So the series and the function match up almost exactly at 0.2 because the error is like barely quantifiable. If I tried a different x value, say x equals 0.8, I should have more error because remember this is centered around x equals 0. So the further I get away from x equals 0, the more the two functions aren't going to match up because I cut the series off at the fourth partial sum. So if x equals 0.8 and I plug that into the remainder formula, I get an error of 2.265. Still not terrible, whatever, but that's what the error is. Now remember, these are geometric series. Geometric series only converge when x is between 1 and -1. So recall, the original series converges when x is between -1 and 1. So obviously the closer we get to 1, the more error there is. This doesn't hold for anything beyond 1. It's only going to hold from x being -1 to 1, because anything other than that, the series don't converge at all, and the error is going to be ridiculous. Okay, so that is error for a geometric series, and then we're going to look at error for a Taylor series, which is more complicated. So go to the next video.